Welcome back. We're in Projectiles unit, worksheet 3, number 2. George is walking to school after it rained the night before. As he walks, he tried to jump over puddles. Isn't that fun? And when he jumps, his velocity has a horizontal component of 3 meters per second, and he reaches a maximum height of 0.2 meters. Find George's velocity in the initial vertical velocity. And B, if the puddle is 1.5 meters long, where will George land? Is he going to land in the puddle? Interesting question. So let's go ahead and let's draw a little picture here. Let's see if I can draw a little boy George here. Jumping. Where would your hands be before you jump? Well, maybe he's like right about to jump. So his hands, he's right about to leave the ground there. So his hands are up already. And here's George. And we'll make a little puddle here. The puddle is 1.5 meters long, so let's give it some like dimension here so I can actually see it. He's not a total flatlander. That is 1.5 meters long there. You know that that's going to be a delta x there for the puddle anyways. Who knows what his delta x will be. And what else can I label? Maybe we don't really know his path, so I'm not going to really draw his total path here. He does read him. Well, maybe I'll sketch out his mag. I'm gonna guess that he lands after it, and so that's my guess. I can always change it later. We know that the maximum height. I want to do that because now I can put in his maximum height here. His maximum height is from here, and so that's delta y. Maybe I'll put a max on that. Is 0.20 meters. Great. He has a horizontal component of 3 meters per second for his velocity. So if I go and put these velocity vectors here, right at the top, you know that he's not moving up or down at the top, but he is still moving to the right. And so his v, maybe I'll even put x there just to be extra explicit about that, is 3 meters per second to the right. And now you could do this with the left, and it would be the exact same if you drew the picture in mirror image here. Find George's initial vertical velocity, and then where is he going to land here? Cool. Now this one's different because we have like different givens here, but I don't worry about any of that stuff. I go, hey, all of the tricks that I've learned, I bet I'll be able to massage these algebraic equations to be able to figure out what's going on here. So, anyways, in this one, normally I start in the x dimension, but I don't really know anything in the x dimension, so I'm going to go ahead and start in the y dimension. Give myself more room to work in the y dimension because, man, I've done these a bunch, and I seem to have always more calculations in the y dimension, not as many in the x dimension. So it just seems to work out well that way. So we look here and we go, hey, I know the acceleration in the vertical dimension because we've done a bunch of these. The gravity's pulling on that thing, so that's negative 9.8. I don't know the time here. Great. I don't know the original velocity, so now I have a lot of variables. And do I know delta y? Well, I know delta y at the peak there, so let's go do this at the peak. So like at, oh gosh, that's a bad at. We'll do at peak. So now if we do it at the peak, yeah, my acceleration's still there. I still don't know the time, but I do know the delta y, which would be like a max, and now that's 0.2. Okay, cool. Well, that's helpful because now I just don't know two variables. Okay, so I got made a little bit of progress, but I still can't solve that. So then I think to myself, well, maybe I know something else in the y dimension, and I'm still in the y dimension, so maybe I'll extend that over. I'm just separating calculations here. I know v is equal to at plus v naught, and let's look at that equation. So if I'm looking in the y dimension at the end, well, again, if we're doing this at the peak, then this is my vertical velocity, which we said was 0 up and down there. I still know the acceleration is negative 9.8, and I don't know the time, and I don't know that velocity there. So now I look at this and I go, hey, wait, I don't know the initial velocity, and I don't know the time in both of these equations. So I can't solve either one by itself, but two equations with two unknowns, I sure can solve that. So I'm going to go ahead and do that. Let me go rearrange this one. So now the question is, am I going to solve for t, or am I going to solve for v naught there? And I don't know, let's put it in and see what it looks like. So 0 is equal to negative 9.8 t plus my v naught there. Pretty easy to solve for v naught. Move v naught to the other side, but then multiply everything by a negative. So I have v naught, positive v naught is equal to then a positive 9.8 t, because I move v naught over to the other side, it gets a negative, and then multiply everything by negative 1. That looks pretty clean to me. The other way would be divide by your 9.8 there, and now you have t is equal to v naught over 9.8. So just sometimes the algebra is a little bit easier one way versus the other. I think v naught's going to be nice because v naught I only need to put it in one space there, and then I solve for t. If I put in t, then I got to square this thing. One of the 9.8s is going to cancel out there. I think that's going to be a little bit messier. So, and it doesn't matter. You'll get the same answer both ways. But I'm going to go ahead and I'm going to put in my v naught into there. So sometimes you can save yourself a little bit of time and effort by just thinking about, hey, which way might be a little bit mathematically easier. Sometimes it's like a clear winner, and other times maybe it's about the same. So I don't know t, but I do know v naught now. That's 9.8 t, and then multiplied by the t that's right there, right? The 9.8 t is my v naught, and then multiplied by t. So now when I look at this, oh, that actually cleans up really nicely, because if I'm going to leave that half there, I'd rewrite that half 9.8 t squared, and because I don't know if you see this, I have 9.8 t times t, so that's 9.8 t squared. So now I look at this right side and go, man, that cleans up super nice. I have half, right? Look, I have a positive 9.8 t squared, and then I have a negative 9.8 t squared, but just half of that. So I have half of the negative of the same exact thing, so it just gives me half of the positive 9.8 t squared. Okay, cool, sweet. So that simplifies very nicely. That's still equal to 0.2, so I'm just doing my algebra here. And now I just go and solve this and multiply by 2 to get 0.4 on that side, divided by my 9.8, and that's equal to t squared. Let me just go take the square root of both sides there. And so I have t is equal to that. So now my total time in the air, grab my calculator, that becomes a super simple one. Glad I solved for v naught and put that in. and now I get the time is 0.20, and I'll go ahead and put a 2 on there so it separates it from my delta y, otherwise I might get confused. And that's my total time, and let me put the peak there so I remember that that's the time to the peak, not the time back down to the ground. Okay. Now, was that useful? Well, let's see what we're trying to find. We're trying to find the initial vertical velocity, and then where does he land in this puddle here. So I found the time, but then notice that I have this equation. Well, I have these two equations, I should say, which are the exact same equation, just rewritten. And so now I can take that time and I can plug it back in for there. There we go. And now I can find the velocity there. So the velocity is equal to 9.8 times the time, which is 0.202. And I don't use the rounded value. I'm storing that time as t in my calculator, multiplying it by 9.8. And I find that that's 1.98 meters per second is my initial vertical velocity. I'm going to put a v, not y, on there, just so I remind myself that I am working in the y dimension there. And then I could even put that on my picture, because maybe that would be helpful. Sometimes it's helpful for me to be able to see these things. And if I draw it real small here, it's going to get lost on top of him. So I'm going to draw it like that as 1.98 meters per second. And that's my v naught y. Okay, and so then my v naught x there, v naught x, we already know, nothing's pushing or pulling it left or right, so it's got to still be the exact same. The velocity in the x direction is always going to be the same unless you have air resistance or a rocket on there, something strange like that. So, and I'm just asking myself, hey, what is the original v naught of there as well? Maybe some other problem would ask that. I'm not going to go solve that because it doesn't explicitly ask that. So if the puddle is 1.5 meters long, where will George land? Will he land in the puddle? So here we just want to figure out what is delta x here. So then I go to my x dimension here. So now I actually care about something there. It's 1/2 at squared plus v naught t. And you've probably done enough of these that you're going, hey, there's no acceleration in the x dimension, so that whole term is 0. So that greatly simplifies this. And delta x is just my original velocity in the x dimension multiplied by the time there. And I know what my original velocity in the x dimension is. That is just 3 meters per second, as it gave in the problem. So I need to multiply it by the time. Okay, great. Well, let's think about this for a second. Do I know the time? Well, kind of. I know the time to the peak. Well, now here's a trick. We look at this and we go, hey, he makes some parabola. Whether he lands in the puddle or not, he makes a parabola. And if I go and I graph this in the, sorry, not delta y, but in the y dimension going up and t dimension going over here, yeah, he would actually make a parabola there. And he's starting at the height, at one height, 0, let's say, and he's ending at the exact same height. Oh, cool. Well, if you're ending at the same height, you know that parabolas have a line of symmetry that go down the middle. It takes 0.202 seconds to get here. Well, then how long does it take to get over to there? And you go, well, it's symmetric there. So if I just take that time and I multiply it by 2, and not the rounded 2.0 or 0.202, but in the whole value there, I get 0.404 seconds. Is that the whole time for him to get to the end of the ground? And you'd say, yeah, it is. It is. Now that's a trick that only works when you're starting and ending at the exact same height, which we are in this case. So sweet. So I can just put in, I can multiply 2 times the time to the peak there, you might say, and that's equal to my time value there. So I'm going to go ahead and put that in. So I'm just multiplying that 0.202 times 2 and get 0.404, and that's where I got that from. So I multiply that 0.404, which is my total time, multiplied by the 3 meters per second, and I get 1.21 meters, since that's a delta x there, and that's the 1.21 meters. So will he clear the puddle? Well, the puddle is 1.5 meters long, so he is going to land in the puddle. Land in puddle. Lands in puddle. And maybe he loves that, because that maybe he wanted it. Maybe he was looking for a challenge to see if he can get over. And if he got over, big smiles, because he made it. And if he didn't make it over, big smiles, because we're jumping in puddles. And I boxed that too, because that was part of the question: is does he land in the puddle there? So so yeah, did we get everything? Let's reread the problem here. Initial vertical velocity, we got that. And does he land in the puddle or not? Where does he land? We got that too. Where's my initial vertical velocity? That one's this one right here. Maybe I'll put that in a box there as well, because that was part of my final answer. And the circle ones were kind of like intermediate. All right, that's it. Have a beautiful day. See ya.